So now we're going to prove this big result, Chebyshev's inequality, that ends up being kind of a foundational result in random variables and for a lot of statistical procedures and basic results of statistics. They're kind of founded on things that depend on Chebyshev's inequality. So here it is. If you have a random variable x, it could be discrete or continuous. I'm going to prove it for continuous in the continuous case, but it's still true for the discrete case. If the expected value and the variance of that random variable are defined, the probability the random variable ends up within k standard deviations of its mean, of its expected value, is at least this thing, 1 minus 1 over k squared. So in particular, if you take k to be 2, this comes out to be 1 minus 1/4, which is 3/4. So the probability any random variable is within 2 standard deviations of its mean is at least 75%, at least 3/4. It is impossible to create a random variable with a distribution that violates that. No matter what crazy curve you draw for its PDF, if the thing is really a PDF, encloses an area of 1, always positive, then the probability the random variable ends up within 2 standard deviations of its mean has to be at least 75%, usually much more, but it has to be at least 75%. And so the reason Chebyshev's inequality is so useful is because it gives you some bounds on where you find the values of a random variable. I'll give you a really simple example of a consequence of Chebyshev's inequality at the end. So first, let's prove this. So the idea of the proof, imagine you have this random variable and you have its PDF. Imagine looking at its PDF. And we're going to break up the area under the PDF into 3 pieces, okay? Piece number 1 is going to be in here, piece number 2 is going to be in here, and piece number 3 is going to be here. So here I'm using these symbols mu x and sigma x, mu x, sigma x, mu x, mu x, sigma x, for the expected value and the standard deviation. So this symbol, mu x, and this symbol, it's the same thing. The expected value is the same thing here and here. And this thing, the sigma x, it's the standard deviation. It's the square root of the variance. So these aren't the same thing, but this one's the square root of that one. Okay, so this is the mean minus k standard deviations and the mean plus k standard deviations. So we're taking the real number line and we're saying the mean is somewhere. Divide the area under the PDF up into these 3 pieces. The piece which is less than the mean minus k standard deviations, the piece which is between, or rather, better way to say it, within k standard deviations of the mean, and the piece which is more than k standard deviations above the mean. All right. So the proof goes like this. Imagine you're going to calculate the variance of x, and you'll see why I'm going to consider the variance of x in a sec. So the variance of x is going to be the integral over the whole real number line of x minus mu x, I'm going to put a little x, whoops, capital X there, mu x squared times the PDF, there you go, dx. Okay, so something we can say is that if you look at this integral, when we're doing this integral, we're going over the whole real number line. And inside this integral, the thing you're integrating, it's never negative. It's non-negative because this thing is a square, whatever, something's getting squared, so it can't end up negative. And this thing is a PDF, so it can't end up negative. And if you take 2 non-negative things and you multiply them, you get another thing that's non-negative. So therefore, the value of this integral has to be bigger than or equal to if you were to integrate the same thing, but instead of integrating it over the whole real number line, you just integrate on these 2 pieces, the outside pieces, the piece from minus infinity to mu minus k standard deviations, and the piece from mu plus k standard deviations out to infinity. Right? Because if you integrate something that's always positive, then the bigger area you integrate in, the bigger the value of the integral is going to be. If you reduce this domain of integration, then the results can only be smaller. because you're integrating a thing that's always positive. Okay, so therefore this is less than or equal to the integral from minus infinity up to here, mu x minus k sigma x of the same thing, plus the same integral but on this region over here from mu x plus k sigma x out to infinity. X minus mu x, oh, apologies. Little x minus mu big X squared times f big X at little x d little x. Okay, good. So the variance is bigger than or equal to the sum of these two integrals. All right, now here we go. Because let's consider this integral, the integral on the 1 region and the integral on the 3 region. So on region number 1, okay? On region number 1, the value of little x. Let's do actually region number 3. The same argument can be made for region number 1, but then we're going to have to deal with negatives. So I'll do the simpler one first. On region number 3 here, the value of x, little x, our variable on the real number line. So you can see that, yeah, little x, that's my variable right here. The value of this variable on the real number line has got to be bigger than or equal to mu x plus k sigma x. So bigger than or equal to mu x plus k sigma x, okay? Because I'm in this region right here. So the value of little x has got to be bigger than or equal to mu x plus k sigma x. But, watch this, what I'm going to do is I'm going to move this mu x to the other side. All right? So I just move the mu x to the other side of this inequality. That's fine. In other words, you subtract mu x on both sides. Now I'm going to square both sides. And now this inequality holds because here I square the left-hand side and I square the right-hand side, but because it's a product, that's the same as squaring both of the factors of the product. And I end up here. Now this works because both of these things are positive, right? I mentioned this before, I think, in an example recently, that it's important to realize that if you have two positive things like 1 and 2, then yes, 1 is less than 2, so 1 squared is less than 2 squared. That's true, because 1 is less than 4. But if you have two negative things, it doesn't work that way, right? Minus 2 is smaller than minus 1, but if I were to square them, I would end up here. Minus 2 squared is 4, minus 1 squared is 1, but this is definitely false. We're not worried about that here, though, because these things on each side, they are both positive. X minus mu x, why is that positive? Because we're over here in region number 3, so we're definitely bigger than the mean. Okay? Why is this side positive? Because k is a number of standard deviations, a positive number, and this is the standard deviation, which is always a positive thing. Good. Okay. So, a similar argument works on region number 1. I'll leave that to you. You'll have to think a bit more about the signs here, but a similar argument will show that on region number 1 is also true. So this inequality, this also holds on region number 1. So now check this out. Now I have bounds here. I know that this thing right here, inside both these integrals, has to be bigger than k squared sigma x squared. Okay, good. And therefore, I can replace both of these guys with k squared sigma x squared, and it's only going to make the value here smaller. So this thing is going to be less than, or this sum of these two integrals is going to be less than or equal to what I would get if I took the same things, I wrote the same thing again, but I replaced each of these guys with k squared sigma x squared. So that's what I'm going to do. So now, continuing our calculation here, we now have that the variance of x, I'm not going to rewrite it again, but yeah, continuing from here, the variance of x is equal to this, which is less than or equal to this, and that is going to be less than or equal to, okay, let's see what I get here. Take the first integral, can you see it? Yeah, so I take the first integral and I replace this with k squared sigma x squared. So minus infinity to mu x minus k sigma x, k squared sigma x squared, fx of little x dx, plus, same thing for the second integral, which the second integral goes from mu x plus k sigma x up to infinity, k squared sigma x squared, fx little x. All right. Now, this is just a number, so I can factor it out of the integral. I'll factor it out of each integral, and then I'll factor it out of the sum. So this is less than or equal to, here we go, k squared sigma x squared, all times the sum of these two integrals. Integral from minus infinity mu x minus k sigma x of the PDF plus the integral from mu x plus k sigma x to infinity of, again, just the PDF. All right. Now we got it. Because what is this? This is just the integral of the PDF. When you integrate the PDF, it gives you a probability. The probability the random variable ends up in that integral, ends up in that interval, right? So this thing right here, this guy right here, this is the probability that our random variable ends up in region number 1. And this guy right here, this is the probability our random variable ends up in region number 3. So therefore, the sum of those two probabilities, it's this area right here. And therefore, let's write it out. Okay, just anyway, it's these areas right here. It's the probability a random variable ends up in the two tails. So this is the probability our random variable ends up less than mu x minus k sigma x, less than or equal to, plus the probability our random variable ends up bigger than or equal to mu x plus k sigma x. I might have messed up the equals. I think I did it the way I did the proof. These should be less than or equal to, greater than or equal to. It doesn't matter because we're doing continuous random variables. We're assuming x is a continuous random variable, and so the probability is the same, whether I put a less than or equal to, and a greater than or equal to. Okay. So finally, we're almost done. Let's look way back at the beginning. What do we start with? We started with the variance of x. That was equal to this integral, which was bigger than or equal to this, which was bigger than or equal to this, which is bigger than, so on. The thing on the left-hand side is the variance of x. So this is still the variance of x. It's been on the left-hand side the whole time. Okay? And the variance of x is also known as sigma x squared. That's been there the whole time. It's always been there. Okay? And now you see what's going to happen. I'm just going to divide both sides by sigma x squared. It's going to go away. Notice that it's a positive number. That's important. Ooh, I put this. That's bad. Sorry. Doesn't make any sense. Sigma x squared. Okay. Right? Yeah. The squared goes on the sigma, not on the x. And then in here, we've got, I'm just going to leave this as it is, the probability x is less than or equal. Oh, let's write it as an interval. How about that? This is the probability x does not lie in the interval. These were the tails, right? 1 and 3. So that's the probability x is not in 2. It's got to be in here and here. If it's not in the middle, it's got to be here or here. So that's the probability x is not in the interval mu x minus k sigma x to mu x plus k sigma x. So after all that, what do we have? We have that 1, because I divided the variance on the side by the variance. Divided something by itself, I get 1. It's less than or equal to k squared times the probability x is not inside this interval. Okay, and so now we're basically done. I'm going to divide both sides by k squared, and we're going to get this, that the probability x is not inside this interval. X minus k sigma x. A lot of symbols here. Oh, and I didn't put a bracket. Don't need it. There we go. The probability x is not in this interval is smaller than or equal to 1 over k squared. And so therefore, the probability x is in the interval. Well, let's just do it to figure it out. The probability that's not in there is 1 minus the probability it is in there. Yeah? X plus k sigma x. Okay. So the probability it's not in there is 1 minus the probability it is in there. And then you see what I'm going to do. I'm going to take this, move it to the other side. I'm going to take this, move it to the other side, and I will end up with the result I want. Chebyshev's inequality as we wrote it at the beginning. X plus k sigma x as bigger than or equal to 1 minus 1 k squared, right? You move this over there, you move that over there. Yeah, you'll end up with here. And that is Chebyshev's inequality. Done. So, Chebyshev's inequality, like I said, turns out to be kind of a important foundational idea in the sense that a lot of basic stuff in statistics, if you ask why it's true, you really want to rigorously prove it, you ultimately end up relying on Chebyshev's inequality. And to give you a really simple example of the power of Chebyshev's inequality, it says that if you're dealing any situation where you're dealing with a random variable, it's really valuable to be able to say, okay, suppose that all I know about this random variable is its mean and its standard deviation. Nothing else. Its mean and its variance. Standard deviation, variance, you can go from one to the other, right? Squaring, square rooting, the same thing. I mean, to know the mean is to know the standard deviation. And the variance is to know the standard deviation and vice versa. So suppose you have a random variable, all you know is the mean and standard deviation. What can you say about it? Chebyshev's inequality gives you something you can say with absolute certainty. Nice example. Suppose that a friend of yours is in a class of 20 people. And on the last test they took, the mean on the test, the average score, was 70, and the standard deviation was maybe 8. I don't know, something like that. And you meet some people from the class. First person tells you, I got a 90. Second person tells you, I got a 90. The third person tells you, I got a 90. The fourth person tells you, I got a 90. At some point, somebody must be lying. If everyone's claiming they got a 90, how many people have to claim they have a 90 for you to be absolutely certain that somebody is lying? At some point it's going to be true, right? Because if all 20 people in the class claim they have a 90, obviously somebody is lying. But the point at which you can be absolutely certain somebody is lying happens before then. And Chebyshev's inequality will give you a bound. You can look in the course notes for an example like that. It's with fish, but it's the same flavor.